All right, this is the lesson on section 9.2, the first part, and in this section we're going to talk about 7 indeterminate forms, and we're going to try to find out how do you evaluate limits when you encounter these things. Now, if you'll remember from earlier in the year, remember that if we were going to take a limit like the limit is x approaches 2 over x squared minus 4 over x minus 2, remember that if you substituted numbers in here, you would just get 0 over 0. And you might remember that I said any limit problem that's worth its salt is going to give you 0 over 0 to start with, because otherwise you could just plug the number in and get the answer, and that would be it. All right, now, I did mention to you at that time that 0 over 0 is an indeterminate form. What we mean by an indeterminate form is that normally when we see a number, like if we see the number 0 over 1, we know that this will be equal to 0 because having the 0 on top of a fraction normally tells us that it's equal to 0. All right, but if we have a 0 on the bottom of a fraction, remember, since you can't divide by 0, what we've been thinking is, okay, well now that's infinity, right? So I've got one indicator here that tells me the size of this is 0. I got another one that tells me the size of it's infinity, and nothing could be farther from each other. Okay, unless you went negative infinity to positive infinity, I suppose. All right, but we have this contradiction in terms just by looking at it. Now, it turns out that there are 7 indeterminate forms, and in the book they divide them into 2 types. All right, the first type has the 0 over 0 as one of them. It has infinity over infinity. It has infinity times 0, and it has infinity minus infinity. Okay, and as we get to examples that illustrate each of those, I'll make some attempt at explaining, why each of those would be indeterminate. Now, there's a second type of indeterminate form, and if you'll notice in all of those, there is a base and there is a power. Okay, so when you have something like 1 to the infinity, 0 to the 0, infinity to the 0, that's going to be our second type of indeterminate form. And again, we will discuss why they're indeterminate at some time. Okay, now, the reason that we divide the problems into these 2 types, or the indeterminate forms into these 2 types, is we're going to encounter 3 different theorems in section 9.2. All right, actually, we're going to encounter 2 theorems, and then like a what they call a rule, but it's actually another theorem. All right, and so the ones that are up here on this top line, they're going to be solved by either using this first theorem we're going to encounter today or the second one. Now, in class today, we're only going to talk about ones that are of this type. All right, and so if we look at this, the first theorem that we're going to encounter here, and on this page here, I called them Theorem 1 and Theorem 2. In the old book, they were called that. It's going to be Theorem 4 here, and this one must be Theorem 5 then. All right, so the first theorem here is L'Hopital's rule in the first form. Now, this is what it says. Suppose that at the number A, f of A and g of A are both 0, and suppose that the derivative of f at A and the derivative of g at A exist, and that the one in the denominator is not 0. All right, then this statement is true. The limit as x approaches, I can't read what that says there. It can either be infinity or it can be A, of f of x over g of x. It should be an A right there. All right, should be f prime of A over g prime of A. All right, so now let's apply that to the problem that I had up on the board just a minute ago. If we do the limit as x approaches infinity of x squared minus 4 over x minus 2, since this gives us 0 over 0, then what we can do is we can take the derivative. So the derivative here would be 2x. The derivative here would be 1. And now we want to evaluate this. I had x approaches infinity here. That's supposed to be x approaches 2 when I did the problem before. All right. So if x is approaching 2, we're going to just put in here x equal 2. And so we would get 2 times 2 is 4 over 1 is 4. All right. Now, let's go back and do this problem the way we used to do it and see if we get the same answer. Remember that what we would do in the old days, we'd do the limit as x approaches 2. We would factor the numerator, so we'd get x plus 2 and x minus 2. And then we'd have our x minus 2 down here. We would cancel those because when we take a limit, we're not interested in what happens at this number. We're just interested in what happens at values of x close to that number. So we would put this 2 into what remains, and 2 plus 2 is 4. And so notice that the answer we got by, quote, the old method is the same that we would get here by this thing that is called L'Hopital's rule. Okay? Now, first of all, is there any question about what we did to get the answer doing it this way? Okay, so now, there is something that you need to make sure that you understand. You do not, just as soon as you see a limit, automatically take the derivatives. Because if this thing is not in the form 0 over 0, all right, or one of those other type 1 forms, infinity over infinity, infinity times 0, or infinity minus infinity, if it isn't that, if you were to just plug in the numbers, then you can't use this rule. Okay? So, but anyway, that's a correct way to do that problem. Now, let's look at this next one for a minute. What we're going to do here is we're going to prove L'Hopital's rule based on a graphical argument here. All right, so it says if we zoom in on the graphs of f of x and g of x at the point A, f of a. So right here, this is the point A, f of a, and remember that f of a is equal to g of a. All right, now remember that when you zoom in on a graph, if it's a differentiable function, if you zoom in enough, a graph is, quote, locally linear. So this graph, if I zoom in far enough, is going to look like a straight line. And so is this one. But they look like two different straight lines. Okay? All right. So now it says if we will let M1 and M2 be the slopes of the two lines for these respectively, then for values of x near A, then we would get this. And they just write here what f of x over f of a is. And how we're going to write this is we're going to say for values near A, this could be f of x over x minus a. Now, let me show you how they're getting that. Take this ordered pair right here. This is this is x f of x for a value of x that is near A. Now, remember that this ordered pair here is a f of a, all right? But it's also a g of a because these two things right here are equal, all right? And so what we could do is we could just say, let's move the graph down and just call this value right here 0, all right? So in other words, it says if we zoom in on those graphs at AF of A equals AG of A, then, let's see, in the beginning, remember it told us that if F of A equals G of A equals 0, because that's how we got our 0 over to start with, then these two numbers right here are 0. All right, so now, if I do the slope formula right here on this one, this will be F of X, all right, minus that y value of 0, and then I'll get x minus a, and so that's this thing that we have right here. All right, now, if I do the slope on this other one right here, you know, where I'm going to go this is the ordered pair here, A, G of A. So I'm going to go G, I'm sorry, it's where I'm saying A, it's X right there. So I'm going to go G of X minus the Y coordinate here, which is 0, over X minus A. So that gives me what they have here. All right, now, if this is a slope, that's a slope. So we're saying that right here, the ratio of f of x to g of x is equal to that. Now, it's almost like you'll understand this better if you read it right to left. If we do the ratio of the slopes, that would be this. All right? If I invert this and multiply, then I would get this. Okay? So it's telling me that's the ratio of those. And so it's saying that ratio is equal to the ratio of the slopes. But remember, the slope, when it approaches there, that slope should be equal to the derivative, right? When it's locally linear, it should give me the value of the derivative at A. That slope should. And so what we would be saying here then is if I took the limit of this as x approaches A, then it'll be equal to the limit of the slopes, but another name for the slope there is the derivative, so it's the ratio of the derivatives. So they use that as their argument for that. Now, there is another argument for it that's a more classical kind of proof. All right, and so if you're going to do the classical proof, you want to show that it's f prime of A over g prime of A. So if we would just start with this and then apply the definition of f prime of A, remember, is this. It's equal to the limit as x approaches A of f of x minus f of A over x minus A. Okay, so what they've done up here is they just put that expression in place of this. Now, if we had g prime of A, then it would be this. All right, now, what we have here is the quotient of two limits. And if we have the quotient of two limits, it's the same as the limit of the quotient. So my quotient is that fraction over this one. Let's see, the people that are having to view this won't see that. So it's these two. Now, if I write that, if I flip this one and multiply, the x minus a's are going to cancel, and so it becomes this. All right. Now, f of a and g of a were both 0. So this is a 0, this is a 0. So that's how they get that step, and so that becomes the limit as x approaches A of f of x over g of x. So this is the thing we normally start with, and this is what we end up with, but in doing the proof, we just had to establish the equality, so it was easier to start with this one and get that one. Okay? But now, that's a proof that tells you that this first form of L'Hopital's rule definitely produces a right answer. Okay? Now, let's do a few problems with this. All right. If we have this, we need to write that this will be equal to the derivative of sine. What's the derivative of sine? All right, it'll be cosine, and now we need to evaluate it at this number. Okay. Now, what's the derivative of x? All right, 1. All right, now, what's the cosine of 0? All right, 1. And so we get 1 over 1, which is 1. Now, you may remember at the beginning of the year, one of the very first limit problems we did, we had to use a calculator for this one, but we did that thing about the limit as x approaches 0 of sine x over x was 1. We did not know anything about L'Hopital's rule then, therefore we had no other way of doing the problem, but now we can just L'Hopital that and get that answer and believe that it's correct. All right, would you do the second? I'll give you just a little bit of time to get ahead and work on it. So take the derivative and evaluate the derivative at 0. Actually, let me get you to stop for a second. All right, the reason I'm going to ask you to stop is you need to see that this is an indeterminate form to start with. I should go back up here. In other words, if we've got sine x over x, if we put a 0 in, we get sine of 0 over 0, and so that gives us 0 over 0. You do need to check that the original thing is indeterminate before you just start carelessly doing the rule. Because if it's not indeterminate to start with, then it doesn't tell us, L'Hopital's rule doesn't tell us it'll get the answer. L'Hopital's rule just says, if you have that indeterminate form 0 over 0, we can get it. So now, first of all, if you just plug a 0 in these two positions right here, does that give you 0 over 0? All right, several people are shaking their head yes. Okay, now, once we've established that that happens, now, take a derivative of the top, and then take the derivative of the bottom, and evaluate them at 0. What's the derivative of the top? All right, 1 over 2 times the square root of 1 plus x. Now, if you weren't thinking real clear about this, remember the original right here is this. And so now if we just do 1/2, and then we do 1 plus x to 1 less power, and then the derivative of the inside part there is a 1, then we're going to get what Taylor called out. All right, now the derivative of the bottom is 1. Now we need to evaluate this top expression at 0. So when we put a 0 in here, that's a 1/2, right? And then it's over 1, and so we get 1/2. Right? Now, here's an interesting part about that problem, and one of the reasons why I want you to like L'Hopital's rule. If you first look at that problem, does it appear like it's going to be a hard problem? It does, because it's just a strange expression, right? And one of the things that you're going to see on the AP exam is they'll give you a strange expression and ask you to do something to it. And so the reason that we practice with so many of these is after a while, strange looks normal, if that makes sense. And so we just realize, okay, now wait a minute. We know that if I get that 0 here and the 0 on top, that fits L'Hopital's situation, so we can L'Hopital it. All right, now, check first to see that this gives you 0 over 0. If I put in pi over 2 here on the bottom, I get pi over 2 minus pi over 2, which is 0. Okay, but now up on top, what's the cosine of pi over 2? All right, it's 0, right? But this is 1 plus the cosine, so this is 1. All right, now, is that an indeterminate form? It's not, because indeterminate forms are 0 over 0, infinity over infinity, right? There were the 4 of them that were type 1. This is not an indeterminate form, so what does it mean this limit is? What's 1 over 0 in normal fault pattern? All right, it's going to be infinity. All right, so we'd say that's infinity, or you could say the limit doesn't exist, but it means that this quantity is approaching infinity when this happens. Okay, now, the reason for throwing this problem into the mix here is that thou shalt check that it's indeterminate before you apply L'Hopital's rule. If you don't, you're going to wind up getting something that's not correct because it was not a time to apply it and you have applied it anyway. I feel like when I'm talking into this headset that I'm preaching at something. I don't mean for it to sound that way in case it does. All right, now, in this last one here, is this the form 0 over 0 if you just plug in 0 for x? All right, it is. So now if we take the derivative, we're going to get 3x squared, all right, minus 4. And then here we're going to get 2x minus 2. Okay, now when we plug in 0, what are we going to get as the answer this time? So we're going to evaluate this at x equals 0. And what do we get? Sean, what's the answer here? All right, 2. Okay. All right, now anybody with any questions about that? So the point I want to make is that, hey, it does get answers. Now, there's all kinds of little things that can be flying through your mind on these, and I want to warn you about one of them. How many of you, when you first saw this problem right here, the first thing that went to your mind was that value is bigger than this one, and you thought infinity? Anybody? All right, because it's a very common thought. All right, where would the limit need to be taken for the fact that that's 3 and this is 2 to cause this to be infinity? All right, it'd have to be as x approaches infinity. Because remember when we had those things before, we did the limit as x approaches infinity, and then we had like ax to the m o and plus dot dot dot, and ax to the n. And remember, in that case, when it was approaching infinity, it mattered which of these two, m and n, was bigger. And then we could either get that it was infinity, the ratio of, where I put that second a, let me put a b, the ratio a to b, or we could get that it was 0 if the power on the bottom was bigger. So you have to be careful not to read an infinity into something that's not there. Okay, now, let's go to the next part. All right, sometimes when we apply Rule 1, we still have an indeterminate form. In other words, it could still come out to be 0 over 0 or one of the others that are considered to be type 1. And so we would need to apply the rule again. And so what we're going to say in this form, which is going to be called the stronger form of L'Hopital's rule, is that you can apply the rule over and over and over until you get something that's not indeterminate. Now, because you are going to have to apply it over and over, then right here, you need to put the word limit on this side to make the rule be different than the other one. Because the other one was basically saying, if you just do the derivative one time, what you get is the answer to that derivative quotient is the answer to the problem. But this time is allowing for the fact that if I got 0 for the first derivative and 0 for the first derivative here, then I could just continue the problem thinking of this as the new function, and I could take the derivative of it. So if we apply L'Hopital's rule and we get an indeterminate form, we just have to keep applying L'Hopital's rule till we no longer get an indeterminate form. All right, so let's look at this. Suppose we had this one. We do the limit as x approaches infinity of x squared over e to the x. All right, now, because we're concerned that we might have to apply it more than once, then I'm going to tell you we could just go back here and write limit as x approaches infinity and then put the answer. Okay, now let me back up a little bit. All right, once you know the second form of L'Hopital's rule, then normally you just apply it as the thing that you do. So if we were doing this first problem right here, then we could say this, we could just come over here and go, it's the limit as x approaches 0, and then just put cosine of x there over 1. And now we're going to evaluate this, and if it's not indeterminate, we're done. But if it gave us 0 over 0, we would just write equals the limit, and we'd take the derivative of these two things. Okay? So we will just be doing a repetitive process. Okay? So, Sean, help me out here. What's the derivative of the top? All right, Sean said 2x for those of you listening. And the derivative of the bottom. What's the derivative of the x? No. Jake, what's the derivative of e to the x? All right, it's e to the x. Remember, this is the one where it's its own derivative. All right? I don't want to say shame on you, but that's one of those things of, hey, it's there. Okay? Now, let's see. Let's go back to the beginning again, because I allowed us to skip something. Is this 0 over 0 to start with? Right? No? Because if you put in an infinity here, do you see I'm getting infinity squared over e to the infinity? So do you see that in some sense that's infinity over infinity? But that's an indeterminate form. So in other words, if the top and the bottom both get infinitely large, then it's an infinity over infinity kind, and now we've got to keep going. And so like right here, when we pick this one up, do we still have infinity over infinity? All right, so yeah, all right, so this one's still infinity over infinity. So what does that tell us to do? All right, do it one more time. Okay, so we're going to do the limit as x approaches infinity. All right, now on the top, what are we going to get this time? Alex, what are we going to get as the top one? All right, 2. And on the bottom, all right, e to the x. Now, is this indeterminate now? Do we still have infinity over infinity? I know. All right, we basically have 2 over infinity, right? What's another name for 2 over infinity? All right, 0. Okay? In other words, if you've got a constant on top, you got something that gets infinitely large. If you just think of dividing it, then you're going to go out here a heck of a long way before you get anything that's not a 0. So, neighbor, that thing's close to 0. All right, so that limit is 0. All right, any question there? Yes, that's what you do. Now, so in this time, we had to apply the rule twice. All right, now on the test, I will not give you one where you have to apply the rule more than 4 times. Okay? But you may have to apply it more than twice. Okay? Because what I don't want to do is just establish in your mind, okay, if it doesn't work the first time, you do it the second time, and it always works the second time. It doesn't always work the second time. In other words, like, if you were to put here an x to the 5th, instead of an x squared, do you see we'd have a few more derivatives to go? But eventually we're going to get a constant on top, and we're going to get e to the x on the bottom. Now, let's write that out for a minute. Suppose I gave you this. X to the 5th over e to the x. All right? Now, how many of you would just reason the top derivative is going to go down a power each time, so eventually it will be a constant, but the bottom derivative is going to stay e to the x the whole time. Therefore, after a finite number of applications of the rule, we're going to get a constant over infinity, and therefore it'll be 0. All right? So if you realize that that's true, then you could just come over here and put that it's 0. Now, you might have to explain that to me on the test, you know, how you know you're going to get the constant on top, but you should feel confident that it's 0. Now, one of the things that we're going to learn a little bit later in this chapter is we're going to talk about growth rates of functions, all right? And we're going to talk about one function growing slower than another one, all right? And so once we get to that, you would say, this function's growing slower than that one. So if we do the limit as x approaches infinity, if the one on the bottom grows faster than the one on the top, that's always going to be 0. We'll eventually get to that. Sabrina, have you done that already? Have you had that as a theorem already? Somewhere? Okay. Okay. All right. Now, would you all work this one? Before you go flying in there, check and see if it's indeterminate. Does it give you 0 over 0? You get a square root of 1, minus a 1, minus a 0, over a 0, for 0 over 0, right? Okay. Now, let me ask another question, because, you know, sometimes if you think before you start your pencil writing, what's the maximum number of times we could wind up taking a derivative in this one? Or what's the maximum number of times we could apply L'Hopital's rule? All right, apply once. Okay. All right, this term won't, but this one will. Okay. All right, apply twice. Okay, in other words, down here, the first time you do the derivative, you're going to get a 2x. The next time you'll get a 2. And once you get a number, if you get just a number that's not 0, it's not infinite, once you get a number in one place or the other, and that's all that's there, then the answer comes in that step every time. So in this one, because once you start doing this one, you might think, wait, this numerator could go on forever. All right. But the denominator down here, once you apply this twice, you're going to have a constant. Okay, now do the work for that. And I'm going to start writing stuff up here. so that the people watching the video don't have to wait forever, but just do it on your paper and then we'll check the answer. All right. Now right here we're going to think of this as being 1 plus x to the 1/2. So we're going to go here 1/2, 1 plus x to the negative 1/2. All right, and then we're going to get minus 1/2. We get the derivative of negative 1 is 0. The derivative of negative x over 2 is negative 1/2. On the bottom, we get 2x. Okay, now if we plug in a 0 for the x in the numerator there, we're going to get 1/2 times 1 to the negative 1/2, but 1 to any one power is 1. All right, and so we're going to get a minus 1/2, and then down on the bottom we're going to get 2 times 0, so we still have an indeterminate form. Okay. Now, because of that, we have to do it again. Put this where it's sort of muted. I was just trying to speak into the microphone where they would hear without having to wait a long time. All right, but does everybody see it's still indeterminate after one iteration of this thing? All right, so now I'm going to start speaking out loud. All right, what we should do is we should take the derivative again. Now, when we take the derivative again, up on top, we're going to get negative 1/4. We're going to get the 1 plus x to 1 less power. But then notice that the minus 1/2 now goes away because the derivative of a constant is 0, and then we get the 2 here. All right, now if we plug in the 0, we've got a negative 1/4, and then we've got a 1 to a power, 1 to any power, again being 1, over 2. So this is negative 1/4 over 2. So that value of that limit is negative 1/8. All right, does anyone in class have a question about that? Does this seem relatively straightforward to you? In other words, you do have to check to see that it's indeterminate. Then you just take the derivative of the top, the derivative of the bottom. Notice that you do not use product rule or quotient rule. I should have just said you do not use quotient rule. In other words, you got a fraction, but you're not taking the derivative of the expression. You're just doing the derivative of the top, the derivative of the bottom. All right? Now, L'Hopital's rule also works for one-sided limits and for limits as x approaches infinity. All right, so in this first slide, I put this out here so you wouldn't have to do as much copying. It says, evaluate the limit as x approaches 0 from the positive side of sine of x over x squared. All right, now, if we do this one, because they tell us, I'm telling you up here, that it's okay to say that it's approaching 0 from the positive side. Okay, now, when we're approaching 0 from the positive side, I have the graph of it drawn here. Do you see the graph's doing that number right there? What do you think this limit's probably going to turn out to be? Anybody? All right, positive infinity. Now, because on the right side it goes up towards positive infinity, but because on the downside it goes down towards negative infinity, then it would not be logical for us to ask you to do that limit as x approaches 0. So we need to do a one-sided limit there. Okay, and so if I have that problem, now I'm going to just put the equals here, and this was 0 over 0, so now we're going to get a cosine of x here, and then we're going to get a 2x. All right, so now when I put the 0 in, notice that this becomes a 1. And as soon as I get a number in either the numerator or the denominator that's not 0 or is not the infinity sign, the answer's occurring in that step. So right here, I get 0, 1 over 0 is infinity. All right, now look at the B part to this one. Suppose we were approaching infinity from the negative side. All right, we have to think a little bit more on this one. Or we're approaching zero from the negative side. I said infinity there a second ago. All right. The original is still 0 over 0. So if I apply the rule, so this is first application of the rule, I'm going to get cosine of x over 2x like before. Now, here's where we have to be careful. The cosine is a continuous function at 0, and the cosine's value there is going to be 1. So if I'm approaching it from positive or negative, I still get a 1. But now, if I'm approaching 0 from the left, all right, this is going to be close to 0, but until I get to exactly 0, do you see that this is a negative quantity? There's 2 and put in a negative number would be negative. So what we're going to have to think of there is we're going to have to think of that as 1 over the negative of 0. All right? And now, if we do that, we get negative infinity, and you can see from the graph here that that's what's really happening. If we approach 0 from the negative side here, we're on that branch of the graph, which is going down to negative infinity. All right? Any question about that one? Okay? All right? Would you do this one? The limit as x approaches infinity of this. All right? Now, this is just the example of it's okay to take the limit as x approaches infinity as opposed to x approaching a. In other words, L'Hopital's rule works out for positive infinity and negative infinity like it did for the other. Now, when I get this, if I put an infinity in that step right there, do you still see that I still have infinity over infinity? Oh, I'm sorry, it did. My fault. You're right. Okay. Now, all right, it's not going to make a difference in the final answer, but you're correct. All right, now, if I put the infinity in, do you still see that I have an infinity over an infinity? All right, therefore, I must do it again. And so now I'm going to get a 10 over a 6, which is equivalent to 5 over 3. Okay, so now, what I want you to see here, remember in pre-cal, when we had these limits as x approaches infinity, if the two powers were the same, remember how we said it's the ratio of those two coefficients? All right, this in essence acts as a proof of that. We got 5/3 by doing a real set of steps to get the answer. All right, now what this means is there's two ways to do this problem. In other words, there's nothing that you learn in pre-cal that's all of a sudden going to become invalid because we're in calculus. All right, if it was a rule in pre-cal, it's still a rule. So how many of you at the very beginning of this problem just said it's approaching infinity, the powers are the same, so the answer should turn out to be 5/3, before you did any work? Okay, all right, several of you thought that. All right, and so this just validates that that's correct, but you can do it either way. All right, now, some of the samples that we've had so far have been samples that were infinity over infinity, but a lot of the ones that we've had so far have been 0 over 0. So I just put together a few more infinity over infinity samples here. So let's look at them for a minute about why they're infinity over infinity. All right, notice in this first one that x is approaching pi over 2. All right, now, on the tangent graph at pi over 2, all right, remember the tangent curve looks like that, and there's another asymptote over here, negative pi over 2. All right, so as this is approaching pi over 2, the bottom of this thing becomes 1 plus infinity, which would be an infinity. So we're getting an infinity on the bottom. Now, secant is the reciprocal of cosine. Now, I'm going to put negative pi over 2 here and pi over 2 here. Right there's cosine, and it goes up to 1 right there. Secant is the reciprocal of that. So what that means is that if I want to get a graph of the secant, I can take the reciprocal of the cosine values. So where the cosine is 1, the reciprocal of 1 is 1, so I'll get that point on it. Now, over here where the cosine would be a half, then the secant would be 2. And then out here, when the secant gets to be 0, think 0 over 1, reciprocal of 0, 1 is going to be 1 over 0, right? Which would be infinitely large. So this thing's going up like that, and then over here it's going to go up like that. So as we approach pi over 2, this red curve, which is the secant curve, is approaching infinity as well. So what I have there is infinity over infinity. Okay? Now, apply L'Hopital's rule and get us an answer. Taylor, help me out on this one. What's the derivative of the secant? All right, secant x tangent of x is correct. All right, how about the derivative of 1 plus the tangent? All right, it'll be a secant squared x. Okay, now, can I cancel anything here? All right, I can. All right, I can cancel a secant, right? Now, it is okay to cancel, because remember, when you evaluate a limit, you're not interested in what happens at the number. So we're not interested in what happens at pi over 2. All right, and so at pi over 2 is where the infinity is going to occur. All right, and so we can cancel this with one of these. So now what I have here is tangent over secant. Okay, now before we go further, it's hard to look at that, and because the tangent's infinitely large, the secant's infinitely large, but let's see what tangent over secant's equal to. All right, tangent is sine over cosine, right? All right, and then secant is 1 over cosine. Okay, so what does that fraction simplify to? All right, that's the sine. Okay, so another name for this is it's equal to the limit as x approaches pi over 2 of the sine of x. Okay, now, what's that going to be? All right, that's equal to 1. All right, now, I want you to write a note here. When we went from this step to that step, we did not apply L'Hopital's rule in that step. In other words, what we did was we took this expression, went down here, and simplified it. And when we simplified it, then we no longer had something that was indeterminate. Right. Any questions about that? That one. Okay. Now, one of the other things that you're going to realize about this as we go through it is that L'Hopital's rule is going to give you some good practice on remembering the rules of derivatives. And so we'll have that. All right, now, first thought again is x is approaching infinity. What happens to the natural log as x approaches infinity? Does it approach infinity? Natural log graph looks like this. Really looks like it's going out there flat, but remember, one of the things we learned about this one in pre-cal is you can make it bigger than any number, so that means it gets infinitely large. So this one really is also an infinity over infinity. All right, now let's apply the rule. We're going to do limit x approaches infinity. What's the derivative of natural log? All right, 1 over x. And what's the derivative of x? All right, 1. So if I simplify this fraction, because again, all I'm doing is simplifying the fraction, then I get that this is that. Now, what's the value of that? What's the value of that limit? All right, it's going to be 0. This is the first limit thought that most calculus students have, or it's one of the ones that they remember well. Anytime you have a constant over a variable, and the variable is approaching infinity, that ought to give you a 0. Okay. All right. Now, do this one. The limit is x approaches infinity over the natural log of x over 2 square root of x. Now, I put on here to check this answer by graphing just to remind myself to have us do one of those, but do the thing algebraically, and then we'll do it graphically together. Okay, did you get down? Is that correct? Or have I made a little silly mistake? All right, once you get here, what does that fraction reduce to? Because all we've done is we've applied L'Hopital's rule going from there to here. This is just simplifying right here, and we need to simplify again. What does this become? If you invert, in other words, like you got 1 over x, you invert the bottom, you got square root of x over 1, right? Okay, so now this is x to the 1/2 over x, so that's the same as 1 over x to the 1/2, or 1 over the square root of x, right? Is that okay or not? All right, we get the 2 just because it's there. All right, and then if you do the square root of x, remember that's x to the 1/2, so it's 1/2 x to the negative 1/2 right there. So this is 1 over 2 square root of x, and I just wrote it separate like that. And now the 2 is going to cancel one of those, so I've got that. All right, so this is the limit as x approaches infinity of 1 over the square root of x. Now, what's the value of that limit? All right, 0. Okay, now let's look at this one graphically. Let's see. I'm in parametric mode because of something we were doing here. Pre-cal. All right. Now, what we had here to start with was natural log. Wrong button. All right. Natural log of x divided by parentheses 2 square root of x. All right. Now, if we graph this, let's see. I'm just going to go zoom 6 to start with. All right. Notice how it started out being negative here, and then it went up, and it looks like it's barely positive. Now, the question on this one is when it goes up, is it going to keep going up? Remember how the logarithmic function eventually gets to be infinity? All right? Or is it going to stay down? Now, one thought about this, and this is just how I do stuff, when I have to get at it in a hurry. If I want to check to see what something's approaching as x approaches infinity, we've done this sometime this year. I'm going to put in for x min 1,000,000, so 10 to the sixth, and then I'm going to put in for x max 10 to the sixth plus 10. Okay, and then I'm going to have it do the graph. Okay, now when I do this, notice that nothing looks much like it's happening, right? But if you put your trace button on, then you can get a value of y that's there. Now notice that that starts 0.006. So it looks like that thing's going to be approaching 0, but it's still, a little bit up. So if it doesn't convince you that the answer should be 0 here, you could put in 10 to the ninth, and you'll see that you get more zeros. Put in 10 to the 12th, and you'll get more zeros. Now, you have to be a little bit careful when you do that, because after a while, your calculator can only handle numbers that are so big. In other words, once it gets to where, like when you put in 10 to the 13th power with a plus 10 on it, you're having to have 13 digits to represent it, and I think that's approaching the max that the calculator will hold. And so you don't have to go much further than that for it not to be able to do what I was just doing. But this should convince you that the y value is close to 0 as opposed to it going off the top of the screen. If you were to do this, not see a graph, look at a y value here, and it had something like 2.3 e 10 to the 6, then, or 2.3 times 10 e6, or however it writes that, then you'd get the idea that it was going to become infinite. All right. Now, the third kind that we had were examples that are in the form infinity times 0. All right. And now, the thing that I put in here in parentheses is a big deal. Remember, in L'Hopital's rule, you've got to have something where you're doing the limit, and you have to have a quotient. You got to have an f of x over a g of x. So if you have something that is not a quotient to start with, then you must create a quotient. All right? So on this first one, this is the limit as x approaches infinity of x times the sine of 1 over x. All right? Now, on this one, we're going to do this using a substitution of variables, and the only reason for doing this is it makes something fairly easy. And I'll come back and I'll show you how you can not do it that way. But the book in this problem does this thing that I'm going to show you first here. All right. If I were to let h be equal to 1 over x, if I solve this for x, I would get x is equal to 1 over h. And so I could write this. I could write the limit. Now, down here it says x approaches infinity. Well, if I'm going to change this thing to h's, then I would get 1 over h approaches infinity. And then here, I would get 1 over h, and then sine of h. Okay, now, there's some good and maybe some bad. Here's the first thing that's good. I'm going to write the limit, and I'm not going to put what goes down below yet, but do you see that I could write this as sine of h over h, and therefore I have a quotient, because I cannot use L'Hopital's rule unless I have a quotient. This was a product. We were multiplying, all right? And so we need to get it into a quotient. Now, if 1 over h is approaching infinity, what is h approaching to make that be true? It's not a hard question. What would we need to have on the bottom here so that when I divide this bottom and the top, it should be infinite? All right, so it should be approaching 0. Okay, now, anytime you have something approaching 0, it can matter whether it approaches from the positive or the negative side. So right here, when it says here x is approaching infinity, do you see that that means that x is positive? If it's approaching infinity, we can at least assume it's positive. Okay, and so that means that since h is 1 over x, that we want this to be a positive quantity. So we could write here, it's approaching 0 from the positive side. Just in case we run into a circumstance, like, do you remember in this problem here, it mattered whether we approached 0 from the positive side or the negative side? Okay, so we would say there we're approaching 0 from the positive side. All right, so here we could just put here h approaching 0 from the positive side. Okay, now I want to put a little box around this just for emphasis for a minute. When we have things that are infinity times 0, now let's establish this is infinity times 0. If x is approaching infinity here, and that's an x, that's an infinity. Well, and then this becomes times the sine of 1 over infinity, which will be 0, but the sine of 0 is 0, so this original thing's in the form infinity times 0. All right? And so by making the little substitution that we made here, I've created a fraction, and now this just becomes a problem that's a 0 over 0 problem. Okay? And so now I can L'Hopital it, so I'm going to do the limit as h approaches 0 from the positive side, and I'm going to take the derivative of the top and the derivative of the bottom. And now if I plug in the 0 here, I'm going to get 1 over 1, which is 1. All right. Any question about that? I want you to think of this for a minute. I want you to think of how unusual this looks. I've got something that's infinite, and I'm multiplying it by this quantity here. And you know that this quantity has a value between -1 and 1 at all times. And we're saying that that thing approaches 0. Now, the reason that that works is, see, as this is approaching infinity, this thing right here is not oscillating. It's just approaching the number 0. And so in this case, it's almost as if we were declaring this, that for this case at least, infinity times 0 would be 1. Now, it wouldn't be that for everything, but that's a way to do that problem. Now, on this same one, I want to show you a different way to do the same problem so that as you have more methods of attack. All right. Suppose that you didn't think about using this h equals 1 over x thing. If I have to create a quotient here, then do you see that multiplying by x is the same as dividing by 1 over x? So I could write this thing as the limit as x approaches infinity of sine of 1 over x over 1 over x. If you'll think about simplifying that, you'll see that this simplifies to that same expression right there. Okay? Now, let's try to get the answer doing it this way. So, if we do the limit as x approaches infinity, by the way, before we do that, I keep forgetting to make you do this step. If x is approaching infinity, do you see that this is approaching 0, so we get sine of 0, which is 0. This is 0, so we've got a 0 over 0 situation. Every time, before you use L'Hopital's rule, you must check to see that the form is indeterminate. In the homework tonight, just about all of them are going to be, but then all I got to do is put 1 on the test that's not, and you missed 5 points because you didn't check, that kind of thing. So you have to be careful with it. All right? Now, I need help on this one. Sydney, do the derivative of sine of 1 over x. It's chain rule. would you buy negative 1 over x squared? In other words, this is the same as x to the negative 1, so if I take the derivative, it'll be negative 1 x to 1 less power, so it'll be negative 1 over x squared. Okay, so we've got cosine x times negative 1 over x squared. Now, I'm going to put that in a bracket because I don't want anybody to think we can multiply it by that. Negative 1 over x squared there. Okay, now, what are we going to get for this derivative on the bottom? Is the derivative of this 1 over x any different than the derivative of that 1 over x? No. All right, so we're going to get a negative 1 over x squared here. All right, now, next question. Is it legal to go ahead and cancel the negative 1 over x squareds? All right, it is. So we can just cancel those. And so now all we've got is this, the cosine of 1 over x. Now, when x is approaching infinity here, then do you see that this becomes very close to cosine of 0? In other words, that's approaching 0. So it'll be cosine of 0, and the cosine of 0 is 1. Now, remember when we did the problem last time, we got a 1? We get a 1 this time, we just did a different set of steps to get to 1. Okay. All right. Questions, comments? All right. I can tell that it's been a while since y'all have had to sit and listen to me teach, and we've had so many interruptions and all the other things that are going on. All right, because it's almost like the way you respond is a little different. I don't know if it's because of that or if it's because they have the headset on. All right, probably a little bit of both. All right, now let's look at this one for a minute, though. Do you see that we're in the form here of infinity times? Oh, wait, I'm sorry. This will be 0, and this will be negative infinity, right? So if I'm approaching 0 from the positive side, this would be approaching the negative of 0. If I would just plug the 0 in, and then the limit is as this approaches 0 of natural log. Remember on the natural log graph how close to 0 it's negative infinity? So this would be a negative infinity. You got a negative times a negative, so this is one of those infinity times 0 or 0 times infinity cases. All right, now, if we write this one, we're going to go to the limit as x approaches 0 from the positive side. Now, how can I write this and make a quotient? Well, it's going to be easier to take to the bottom the natural log, doing something to get it to the bottom, or to get this to the bottom. All right, the first one, okay? So we could write this as natural log. What would I need to write down here on the bottom so that would simplify back to this? All right, it would be negative 1 over x, okay? Now, do you see that we are now in a form of infinity over infinity, or negative infinity over a negative infinity? Okay, so that's an infinity over infinity. It's an indeterminate form. So now we're going to take the derivatives. So we're doing the limit as x approaches 0 from the positive side. All right, derivative of natural log. All right, 1 over x. All right, now the derivative of negative 1 x to the negative 1, because that's what this is. All right, it's 1 over x squared. All right, Sabrina, what does this fraction simplify to? Okay, it simplifies just to plain old x. Okay, now, is that an indeterminate form? All right, no, we can just plug the 0 in, right, and we get the answer to be 0. All right, any question about the algebra on that? All right, now, let's look at a few examples that are in the form infinity minus infinity. I'll tell you what, we only have a minute. All right, so if you come into an example tonight where there's a minus sign in those two places that I'm just going to tell you, you can hold that and just do it next time, or you can read about it in the text and try to do it, but we'll begin here next time in class. All right, thank you for listening.